Hello again, everyone. Let's talk about evaluating diodes in this session. You're going to be given, from time to time, circuits that you have to evaluate. And so right now what we want to do is we want to focus on deciding what our sort of circuit's order of operations are. When you have math, you have a problem where you need to solve, and there's addition, subtraction, multiplication, division. We have an order of operations, and I think, at least I learned growing up, that was please excuse my dear Aunt Sally. So you have parentheses. What was it? Please excuse exponents. My dear was multiplication and division, and Aunt Sally was addition and subtraction. So you had an order that you went through to see what was done first, what was done second, what was done third. We have the same kind of idea in circuitry. We need to figure our solid state components out first. They're greedy, they're going to take their voltage first. And so we need to find out if they're even going to turn on, because as we found out when we were studying ideal diodes, we had a situation where if the diode was conducting, it was treated like a piece of wire with no resistance. We know in reality that's not true. There's a little resistance, it takes a little voltage, and it's taking some current. The rest goes to our resistor. But first we need to know if it even turns on. If it doesn't turn on, it acts like an open switch. And that open switch has infinite resistance. It won't conduct anything. The electricity can't jump the gap, and so we have possibly an open leg of a circuit, or in certain instances, the whole circuit isn't even turning on. So let's take a look right now at a diode that is conducting, and let's see how it behaves. Okay, so I have a circuit here, and my current path, we learned the electron flow method, comes out of the negative of the battery, it moves to positive. Remember, there's another method called hole flow, and you will see different examples of that on the internet. It's confusing. It will confuse you and everyone that you're talking to if somebody's talking about hole flow versus current flow. So make sure that when you're looking at a drawing that you understand that us technicians live in the material world, and we know that electrons flow towards positive sources, and that's how the world works. Hole flow is an older method of looking at things. It's still widely used by engineers, but it's going to confuse you. So make sure that you understand when you're talking in English and when you're talking in French, so to speak. We're going to talk electron flow. So make sure that if somebody starts talking about something, ask them, especially if they're talking about how the current flows, make sure that you're expressing to them that you know electron flow. And later on, when you get really good at it, you'll learn how to talk both. But for now, let's just stay with electron flow until we're clear. The electrons are flowing from the negative back to the positive source. We know that our diode needs agreement. So when we bring our polarities for our circuit around, we see the internal voltage that our diode comes with. Positive at the anode, negative at the cathode. That's baked into it. If I pull this diode out of the circuit, I will see it still has polarity. If I pull this resistor out of this circuit, I can't tell which side is positive or negative. It picks that up from the circuit that it's in. And now it has it, but if I was to pull it out of this circuit and just grab a bag of resistors, they would not have polarity. Okay? Some components come with baked in polarity and orientation, some don't. Okay? So this diode so far is a go because it's got matching polarities. However, we also need to have enough voltage. If I said that this was a 1/2 volt battery and this was a silicone diode needs 0.7 volts. There's not enough voltage here. The diode's going to try to take all of the voltage and none is going to go to the resistor. You're going to have an open circuit. The diode doesn't have enough to open up, so it's just going to act like an open switch. Okay. As I start to move through 0.5 to 0.6 to 0.7, we have what's called a knee current, and we found out that the diode starts to open up around a rounded logarithmic corner, and this is called the knee. How do we spell knee? K-N-E-E? I don't know. That's a good question. For whatever reason, my brain's not working today. It doesn't matter. There's a knee current, and we know that the voltage starts to open up and the current starts to conduct until it moves into that ideal realm where the voltage doesn't really change much anymore, but the current continues to go up through that curve. Okay, so we have the diode wants to open up, but it needs not only to have polarities in the correct direction, it also needs enough voltage to do so, or enough current to do so. Okay, so let's give our battery this time, let's give it 10 volts. And I'm going to, just because I don't have the room on this little whiteboard here, I'm going to just say 10 volts, but I always want you to say 10.00 VDC. Okay, I want you to use proper engineering notation on the assignments that you give me. It'll be doctor points. VIT, VTIT, RT, V1, I, we'll do R1, I1, V2, I2, R2. All right, so here's our circuit. I'm going to start to break this down. I have enough voltage and my current polarities match what the diode is looking for. So this diode will open up. And since it's greedy, it's going to take its voltage first. Over here, I'm going to express, even on your sheets, you can express volts as 0.7 volts. This is one of the only okay times where I'm going to be okay with you saying something is 0.7. Technically, it should be 700 millivolts, but I don't want to have millivolts and volts all over this. I want it nice and easy for my analysis. So I'm going to say 0.7 and 10, because it's much easier for me to say 10 minus 0.7 equals 9.3 volts DC. Okay, it's easier for me to see what I'm working with. If I have 700 down here and 9.3 over here and they somehow equal 10, that could be a little bit confusing. So we're going to keep our diode at 0.7. We're saying it's silicon. If it was 0.3, it would be what? Germanium, right? So I know the voltage here. My diode took the voltage first, but it needs a current limiting resistor to tell it what to do. So the rest of the voltage then goes here, and I'm just going to say my given is 1 kiloohm. Okay, so if I was given first volts, second resistance over here, the third thing that I discovered was that my voltage over here was 0.7 because it had its polarities. It was able to turn on. It took 0.7 volts. Then my resistor has 9.3 volts because that's what's left in this scenario. So step number 4, I've discovered I have 9.3 milliamps. It's a series circuit all the way around, so I know that I also must have step 5, 9.3 milliamps here, and I must also have 9.3 milliamps here, step 6. Okay, Now I can start to figure a few other things out. Okay. If I really want to get crazy with this, and for this purpose I do, step 7, now I'm going to figure out what is my resistance of my diode. Okay. My resistance of my diode is going to be calculated by taking 0.7 volts divided by 0.90093. I get 75.27 ohms. Okay, so then my RT is actually 1.075 kilo ohms. And you're going to see something like that in your circuit too, because the diode has a variable current, and it's going to have a variable resistance, and that's going to get set based on what happens to your resistor up here. When you find equilibrium, when you actually turn your circuit on, you're going to discover that because of where things settle, you're going to have a little bit of different results, possibly than this. So on my steps, I forgot 2, 3. So this was 4. So I figured out my resistance here. I figured out 5 my current, 6, 7 my current, and then I can go ahead and figure out 8, 9. Okay, so that's how I figure all of this out. All right, that's how you would evaluate a diode for a go. First the diode for voltage, then you give the rest of the voltage to your resistor. Once you have your voltage here, you know your voltage and your resistance, you can calculate out your series current. You can pull your series current through to everyone else, figure out their resistances or powers or whatever you're looking for. If this thing is a no-go, then your diode simply acts like an open switch. If I have a test point and a test point, I should measure source volts across that open switch. In other words, in this case, if it was open, I would measure 10 volts. Okay, that is your diode evaluation. If you have any questions, feel free to email me.